The topic today is intermolecular force. Intermolecular forces. What is intermolecular force? It's a force that acts or that holds molecules together. It's a force between two molecules. Okay? And when it holds them together, then it functions like a unit. The intermolecular, like we see here, this is a molecule, this is a molecule. This force holding these two molecules together is intermolecular force, like you have interstate freeway, between molecules. Okay? Then there's another force here. This force is what we've done before, is a chemical bond, covalent bond, holding two atoms together. This is intramolecular force, intramolecular force. Okay? These are two atoms. The force holding them is intramolecular force, but this is intermolecular force. Look at this. That means this is a weaker force compared to this. Common sense will tell you that. Okay? Another intramolecular force is ionic bond. Like here, you have, we know how ionic bond is formed. You see this bond holding sodium and chlorine together is called ionic bond. There's attraction. You know how electron is transferred from metal to non-metal? When it gets transferred, you have cation and anion, they attract each other. That bond holding together is ionic bond. Here, this is intramolecular force. This is intramolecular force, but this is intramolecular force. Okay, so intramolecular force, there's ionic bond and covalent bond. Both of them are intramolecular force. Okay, this is within atoms or within ion, between, you see, between, is right, between these two atoms, or this one between two ions. Okay, now we are focusing more on intermolecular force, but we already did know, we did covalent bond, which there's a video on that about covalent and ionic bond. We've done that. Hopefully you mastered it. So the main types of intermolecular forces, there's one called dipole-dipole interactions, and there's hydrogen bond, which is a special type of dipole-dipole interactions. Okay, this hydrogen bond is the strongest intermolecular force. It's not actual bonds, just attractive forces. Then we have London forces, which is the weakest. So this London force is in every molecule. Every molecule has London force. I will explain what it is. So the dipole-dipole interactions. So this one is shown here. If you look, this is FCl. There's is polar. Because it's polar molecule, this is partially positive, this is partially negative. It shouldn't be, maybe because they're not able to say partial, but it cannot be plus like ionic bond. It's partial positive, partial negative, because fluorine is more electronegative. So it will draw more electron to itself, making it partial negative. This will be partial positive. Just go back and look at the types of covalent bond. Okay, polar covalent bond, non-polar covalent bond, that will remind you about this. So when this is partially negative, this is partially positive, they attract, and that's the dipole-dipole interaction. That's what it is. Okay, so this is now dipole-dipole is intermolecular force. Intermolecular force, you see how they're attracting between molecules, So here, hydrogen bonding, we looked at which is a special type of dipole-dipole bond. You see that? You have water. Water is a polar molecule also. Now, this will be partial negative. This is partial positive. It's not showing here, but I'll show you simulation on that. And there'll be attraction between this partial negative and partial positive. Then this is hydrogen bond. Okay? And hydrogen bond can also form between hydrogen and fluorine and between hydrogen and nitrogen. Only these two atoms can form hydrogen bond. Only these two. You see that? NH is a hydrogen bond. OH is a hydrogen bond. FH is a hydrogen bond. But I'll show you a better picture of it that will make it. Let's look at hydrogen bonds, okay? This is water. Okay, water has that's is H2O, right? This is oxygen, these two are hydrogen. Remember, this is polar molecule, okay? So let's see what happens. You see that? This is polar molecule. Oxygen is more electronegative than hydrogen, so this will be partial negative, partial positive. See, when it comes contact with another water, you see the hydrogen bond between partial negative and partial positive, between molecules. You see that? Between molecules. This one is between oxygen and hydrogen. That this one is not intermolecular, it's intramolecular. But you see this one with dotted lines? They are intermolecular for this time is hydrogen bond. Hydrogen bond. Okay. So let's if I increase the temperature, let me see what we have. You see, they are moving more. You notice more hydrogen bond forming. They are moving more, so you can see that. Just to show you the again, intermolecular force. These are the one between molecules. You see that? Between partial negative and partial positive of another, of two molecules, then that forms then is much weaker bond than the bond between oxygen and hydrogen, much weaker bond. And there's a London dispersion force. This London dispersion force is very weak. It's the weakest of all the intermolecular forces. And it's in every molecule. Every molecule has, whether polar or non-polar molecule has this London dispersion force. Is very weak and is not permanent, is temporary. So when every molecule move, they vibrate or they move, there's some kind of movement. So when they are moving, there'll be uneven distribution of electrons. And the one that has more electrons will be partial negative, that one that is less electron will have partial positive. But this is temporary, it's not permanent. So because this is partial negative, partial positive, this will attract and form intermolecular force, which is very weak. This is non-polar molecule, but it can form this London dispersion force. I will show you this for better understanding of what is going on. Is instantaneous, is not permanent, is very weak force that is found in all molecules. So is non-polar. If the molecule is non-polar, the only intermolecular forces we have is London dispersion force. It's a between all molecules and atoms. Is the weakest of all the forces, intermolecular forces. So the more the strength of the London dispersion increases with number of electrons in the molecule. The more the number of electrons, the more the London dispersion force. Let's look at these forces, okay? This one is London dispersion force. Let's look at it. You see, this is the London dispersion force. You see, it's not permanent, it's instantaneous. It's not permanent. As soon as there's the you don't have the same number amount of electrons, look at it. Because it's moving, electrons we tend to shift in one side. You see this one will be partial. The one that has more, we have partial negative. The other one have, you see this? Partial negative, partial positive, they attract and forming that. It's instantaneous. Okay? So that's London dispersion force. Let's look at dipole-dipole. Okay, this is dipole-dipole. You see that? This is polar molecule. You see that? This is not, it's not like the other one. This is not temporary. This is dipole-dipole. You see partial positive and partial negative attract. Like the London dispersion force, you see this partial negative is keep on varying and this, it was instantaneous. This is dipole-dipole, partial positive, partial negative. This is happening with polar molecule. Polar molecule, okay? Also, London dispersion force also exists in polar molecule, but the thing is, the main intermolecular force in this one is dipole-dipole. Okay. Okay, this is hydrogen bonding. You've seen this, which is example of dipole-dipole moment. You've seen this before. Look at that. This is the intramolecular force. Oxygen, partial negative. You see, partial positive hydrogen. So this is hydrogen bonding. Okay. You see that? Let's do it again. So the water we use, this is the bond that is holding water molecules together. You see, it looks like a film, okay? There's more to this. There's a video that will tell us the unique properties of water, which is as a result of this hydrogen bonding. Unique properties of water that we're able to have life on Earth is because of this hydrogen bonding. Remember, is the strongest of all the intermolecular forces. Okay. It says explore the different attractive forces. So let's compare polar patch. You see this? Non-polar molecules. So this one has only London dispersion force because the only type of force non-polar molecules have is London dispersion force. Look at it. You see? Very easy to separate. If I reset it, you see that? It's a very weak force. Then let's look at polar. That is dipole-dipole. Okay? These polar molecules form dipole-dipole force, intermolecular force. Look at this. Okay? You see, it's a stronger force than dipole-dipole. I mean, than London dispersion force. So let me reset. You see that? Okay. So let's look at non-polar. Look at this. There's nothing here. There's no partial positive, partial negative here. Look at this. Okay. It's induced dipole attraction. So that's for you to see exactly what we've been talking in theory. Okay. Let's look at this with example of what you just did. So this time we have hydrogen molecule and hydrogen molecule. I hope you know why we call it hydrogen molecule. We didn't say hydrogen atoms. Molecule and hydrogen molecule. Remember the nonpolar and polar covalent bond we did? You have to remember all of that to have a very good understanding of this. So you have to go back and watch the video. Okay, look at this. What type of bond? Let's repeat. This is London dispersion force. Okay. Then this is also London dispersion force. Very weak. You see how easy it is to separate? Okay. This is polar. Polar. Why do you have this aligned this way? Because hydrogen will be partial positive, fluorine will be partial negative, and they will attract. You see that? So this will form, get your answer, more difficult. It's a more stronger. It's dipole-dipole. See that? More stronger than that London dispersion force. Then let's go to this one is that one they say induce this dipole. Okay. So the main thing we are looking at is this London dispersion, how it differs from dipole-dipole. That's the main thing we get out of this. Let's look at examples. Let's look at the examples of forces in this compound. This here, actually, I'm supposed to say CH3, more than one molecule of this, more than one molecule, like 2 molecules of these, 2 molecules. That's the way I'm supposed to ask this question. So we want to look at what force, if I have this and another ethanol, CH3OH, what is not, this is not ethanol, it's not a methanol. This is for me, we want to see how this force between this molecule and another molecule of this, what type of force is between them, what type of force is between this and another molecule of this, what type of force is between this and this. So the first thing you have to try to figure out is what type of molecule is it? Is it polar molecule or non-polar molecule? If it's polar molecule, very likely it will form dipole-dipole. If it's non-polar molecule, very likely it will be London dispersion force. So based on what we already did, in previous videos, you should be able to identify the type of molecule this is. So if this is interacting with the same type of molecule, what type of intermolecular force is it? So let's look at this. So for this, you see this? This is a polar molecule. Because it's polar, this is partial negative, this is partial positive. So when it interacts with other one, this positive, and partial negative interacts. So that's dipole-dipole. Okay? Now, this one is tricky because you have this one, partial negative, partial positive. So this is hydrogen bond. So in this interaction, there's dipole-dipole, there's hydrogen bond. So you have to learn how to draw this. Okay? All you have to understand is looking at a molecule, is it non-polar or polar? If it's polar molecule, you can, in that one each molecule, you can identify which one is more electronegative. The one that is more electronegative will be partial negative, and the one that is less electronegative will be partial positive. The one that is more electronegative pulls the electron towards itself. That's why we did this already. Okay, so this is dipole-dipole. So why is this called hydrogen? Because there's intermolecular force between partial negative and partial positive. Hydrogen bond can form with hydrogen and oxygen, hydrogen and fluorine, hydrogen and nitrogen. Then this one is non-polar, non-polar. Okay? It's a nonpolar molecule, so this is the only bond it forms is London dispersion force. That's the only type of that's the only type of intermolecular force that nonpolar molecules have. London dispersion force, that's the only type. Then this one is polar molecule, so it forms dipole-dipole type of intermolecular force. The same principle. Very, very easy. We watched this video, which really shows you about unique properties of water and why. This is application of all this to real life. The reason water is have these unique properties is because of hydrogen bond. So I want you to pay very good attention to this video. It's very important.
Imagine an Earth without water, life without water. We find it everywhere, in the atmosphere and below our feet. 3/4 of the Earth's surface is covered by this essential liquid. It's a difficult thing to imagine life without water, because our own survival depends on it. In fact, water is vital to the existence of all forms of life on Earth. Water, or H2O, is an unusual compound with amazing properties. These unique properties are what make it so important to life. First of all, water happens to be the only substance on Earth that can be found naturally in all 3 states, as a solid, a liquid, and a gas. It is rare in that it actually expands as a solid, which is why ice can float. Pure water is essentially colorless, odorless, and tasteless. Water has a neutral pH, which means it is neither acidic nor basic. Water has been called the universal solvent because it can dissolve many substances. Wherever water goes, either through the atmosphere, the earth, or through our bodies, it takes along valuable chemicals, minerals, and nutrients. This is one reason why water accounts for about 70% of the weight of a cell, which is the building block of life. Water has high specific heat, which means it absorbs a lot of heat before it changes temperature. This is why water makes a great coolant. This is also why oceans, lakes, and water vapor in the atmosphere help to regulate the Earth's temperature. Water molecules are sticky. They attract to each other, which is why water tends to float together, fall as raindrops, and bead up on the surface of a leaf. This property is the result of cohesion. To understand cohesion, let's imagine we're recreating a water molecule. A water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. Because of the molecule's arrangement and the electronegativity difference between the hydrogen atoms and the oxygen atom, the molecule becomes polar. The oxygen atom has a negative charge, while the hydrogen atoms have a positive charge. Since we all know opposites attract, the oxygen atom will stick to a nearby hydrogen atom. The result is a strong bond. Surface tension is a result of cohesion and is the measure of how difficult it is to break the surface of a liquid. We can observe the high surface tension of water by watching this mosquito step onto its surface, or this insect as it struggles to free itself from a droplet. Surface tension is also what causes a water droplet to take a spherical shape. Water is the most cohesive of all non-metallic liquids. Adhesion is similar to cohesion, but refers to 2 different surfaces or molecules with an attraction to one another. This is why the droplet sticks to this leaf. Along with cohesion, adhesion is responsible for a phenomenon called capillary action. Capillary action is the force that pulls water upward against gravity through a narrow tube. This is an essential property for plants, which rely on capillary action to pull water from their roots up to their leaves. So it's pretty obvious that water is important stuff. Humans rely on it for personal consumption, as well as things like industry, energy production, and agriculture. But we sometimes have a tendency to use more than we need and pollute what's left. We need to make sure we keep it pure and plentiful.
Okay, these are the practice questions. Hopefully the video makes a lot of sense. So identify the main types of intermolecular forces on the following compounds. So by now you know the types of intermolecular forces. Okay. You identify it, pause the video, take your time, go through the examples we did, the simulations that will help you. And then these are the answers. You check if you got them right. Now, I have challenging questions. In this one, I want you to draw it out to see if you really understood it and label the intermolecular force. Whichever one it is it dipole, is this London dispersion force, whichever one it is, you draw it out and label. Then you have to show the two molecules how they are attracting, something like that, like you saw in what we did. Then this one, which one is intermolecular force, which one is intramolecular force? You don't have to draw it. You just look at it and say, okay, if you want to draw it, that's fine, but you're showing the type of force in each of these, okay? You're not saying the type of intermolecular force. Is it intermolecular force or intramolecular force? That's it. Okay, I thank you for watching.